It's oh, then yeah.
It's a typo?
Yes.
Yeah. Okay. I just thought, oh, maybe.
Oh, okay.
I know, like, he has a wife, right? Maybe she's a guy.
No, yeah, that must be.
Okay, we ready? Where's he gone?
He was here.
Yeah, he's.
Should we wait for him?
He went looking for his phone.
Yeah, he'll join me.
Okay, so welcome everyone. So this is a very happy day for Ratnesh. And it's a happy day for me too, but I have kind of mixed feelings because I'm going to miss him. Right? He's been really awesome ever since he got to WinLab and Rutgers, right? And I don't know when it was. He showed up one day in my office and said,
2013, I guess.
yeah, I'd like to work with you, and that's it was a no-brainer for me because you were in my class, right?
Yes.
Yeah, so I wanted to make sure Ivan was here because I want to acknowledge Ivan. He's been as much of an advisor to Ratnesh as I have been, perhaps even a better one than me of late. So Ratnesh has done some very nice work in non-contiguous spectrum access, right? And again, he's one of these unique students who has not only sort of done nice analytical work with rigor, but he's also sort of very good and not afraid to get his hands dirty and work on our test bed, right? Which is why he's a big favorite of Ivan, right? And that's what we're going to really miss about you, right? But Ivan and I were talking about this on our way back. We were down in Maryland for this meeting earlier this week, and on the train we were saying, who's going to replace Ratnesh, right? So have you thought of someone?
I think Neil will show.
Yeah, so anyway, he's done really nice work. I'm going to let him talk about that. And also he's off to a place where the weather will be much nicer, although here we have pretty good weather these days. But perhaps traffic is much worse. So without further ado, Ratnesh.
Yeah. Thanks, Narayan, for the introduction. And thanks everyone for coming to my defense. So I'll talk about my thesis on opportunistic access of non-contiguous spectrum. And more specifically, I'll talk about something called non-contiguous OFDM for dynamic spectrum access. So, okay, I'll straight away jump into. So the agenda would be, initially I'll talk about what is the state of the spectrum and why there is a necessity for non-contiguous OFDM. And then we actually will propose NC-OFDM, non-contiguous OFDM, as a potential solution for access to these kind of spectrums. We'll go into details of NC-OFDM and we'll see what are the challenges associated with it, and we'll try to come up with some solutions. And at the end, I'll talk about security features that we found for the NC-OFDM signal. So, to begin with, we all know the number of wireless devices is increasing. This is just a plot, generic plot, which shows there's a prediction by Cisco which says number of devices which depend on wireless spectrum would increase, will be in billions of devices, and but our wireless spectrum is finite. So what the regulatory bodies such as FCC would do is they either open new bands such as the millimeter wave nowadays, or they open previously restricted bands such as CBRS band and 3.5 gigahertz, or TV whitespace for that matter, or encourage coexistence between different heterogeneous technologies. So that is generally like LTE Wi-Fi coexistence. Lately there's a lot of coexistence with the DoD sort of devices where you have radars coexisting with commercial devices such as LTE or Wi-Fi. So basically we have an environment where there's cognitive, we have this whole network which is based on some sort of cognitive radio, where we have to coexist with maybe a primary user, such as in this case with the DoD case with radars, where we have to let the primary transmission continue. We cannot interfere with that. And then there are other secondary transmission which are similar to us trying to access this spectrum. So we have to coexist with them as well. So going to how the spectrum looks like when in a cognitive radio setup. So generally, let's say we have a total bandwidth available to us, and this is our intended transmission. This link is something we want to transmit. This is transmitter and receiver. So generally what happens is there is already some sort of primary transmission going on which we have to avoid. And similarly, we have some other secondary transmission which we should avoid. We can somehow collaborate with them, but at the end, what spectrum which is available to us will be fragmented like this. So there are multiple ways we can access these spectrum. We can either use single carrier transmission on each of them, or we can have some sort of multi-carrier transmission which would utilize as much spectrum as possible. So for this kind of spectrum where the spectrum is non-contiguous, we propose NC-OFDM as one of the candidates. So just what is NC-OFDM? NC-OFDM is simply a variation of OFDM where we choose not to transmit on some of the subcarriers. And I'll talk about how is it different from regular OFDM and what are the challenges that might come from it. So this is an example of how the NC-OFDM might work in case of two links which are trying to access this spectrum. So this spectrum has been divided into a lot of subchannels. Some of the subchannels have been occupied by primary users, so which is basically unavailable for secondary access. So these two links can potentially allocate the rest of the subchannels in a manner that gives them most throughput. And this allocation may result in sort of non-contiguous allocation. If we do some sort of optimal allocation where we allocate best possible channel for a particular link, we might end up with sort of non-contiguous allocation. So in this sort of scenario, NC-OFDM will be useful. I'll go into details of how NC-OFDM would work. Some practical examples are TV whitespace, because TV whitespace are in general fragmented at any given location. This kind of access would enable multiple access within a given bandwidth. We can allocate different subcarriers to different links and enable multiple access. And as we'll see that it's very easy to dynamically adapt to the changing condition. If you want to change the spectrum allocation to something different, the process is pretty straightforward. Okay, so because, like I mentioned, NC-OFDM is some variation of OFDM, I'll just go over overview of OFDM so that, because the basics of the OFDM apply to NC-OFDM. So in OFDM, when we modulate the bits to, let's say, to IQ samples, that is, when we modulate it to QPS, KQAM or something else, we get these complex numbers. So when these complex numbers come in a stream, the general signal processing that happens is we take n samples, and this n is actually determines how many subcarriers we are dividing the total bandwidth into. So we take n particular samples, we parallelize it, pass it through the IFFT, and we again get, because this is a square matrix, we get n samples at the output. We again convert into serial and add a cyclic prefix to the front of it. This is like a standard OFDM transmitter design. Then you send it to the RF front end to, in this case, transmitter's case, DAC and then antenna. Just opposite of this happens in the receiver, but at the beginning, what we have to do is we calculate frequency and time offset. We do the correction. Then we get an equivalent of this stream at the receiver. Then we have to, because we have calculated this time offset correctly, so we can now identify a particular block with cyclic prefix added to it. So this kind of, once we find this block, we remove the cyclic prefix from this, and then we get a block of n IQ samples. We again parallelize it, feed it to FFT, we get n samples, we again serialize the whole thing, and we get the IQ sample that we had sent. And then it goes, then it's converted into bits, and further decoding can be done. So left of this IFFT and FFT block can be thought of as a frequency domain. So basically here it means that you're feeding the data into n different subcarriers in the frequency domain. So that is something which is important to remember. So in case of NC-OFDM, when I say that we choose to transmit only on some of the subcarrier, it means instead of feeding the data into all of these bins, we can choose to feed the data only on some subset of it. And so So this is the same transceiver design where we have this transmitter, it goes, the data goes through channel and then it's the receiver. So the change that we have to make for NC-OFDM to work is the subcarrier mapping. So the subcarrier mapping, while doing serial to parallel conversion, would decide which subcarriers the data is going into. So this would be the change that would be necessary for implementation of NC-OFDM. So a general question that has been asked to me many times is how is it any different from LTE downlink OFDMA? So even in that case, you can at any given time multiple UEs can be allocated subset of subcarriers. But generally, what happens in that case is there is eNode B present, which provides a tight control of synchronization and scheduling for this kind of to enable the whole communication. And we'll see that if there is no such tight control of synchronization, what challenges that we see. And generally, the spectrum which is allocated, even at a given time, if two users are allocated to different parts of the spectrum, they are generally allocated contiguous bands. So NC-OFDM potentially allows for kind of multiple point-to-point link communication. There are two ways of looking at this network. One is you can think of it can enable multiple point-to-point communication, which can potentially interfere with each other if they were using the same resource. Or you can think of it as a time, like a snapshot in time, where you have, in this case, 4 Wi-Fi service providers, and AP is connected to one particular station. So it can enable, NC-OFDM can enable this sort of communication without, that way it would be different from a regular OFDMA. And in time and frequency, you can potentially, theoretically allocate different number of subcarriers to different users, and they can be non-contiguous, as the name suggests. So why do we want to use NC-OFDM? Because it's a multi-carrier transmission and we can choose to transmit only on some of the subcarriers, it's useful for non-contiguous access. Dynamically adapting the spectrum allocation is also easy, because I mentioned that the only part where we need to make changes is when we do serial to parallel conversion. So at that location, if we simply change the subcarrier allocation, we can dynamically adapt to the spectrum conditions. It has NC-OFDM because it's based on FFT-based design. So there are already efficient FFT-based design, and it has the advantage of one-tap equalization. So NC-OFDM would benefit from that as well. And since we have a well-established ecosystem of OFDM-based transceiver, with some modification, we can potentially enable NC-OFDM-based systems. So when we want to use NC-OFDM, so we want to allocate these non-contiguous spectrum that is available to us. So I'll go into first section where I'll talk about when we allocate this spectrum for to be used for NC-OFDM link, what is the effect of spectrum span? There's like a new parameter comes into picture when we try to allocate spectrum to be used for NC-OFDM. Right. So I'll just talk about what is spectrum span. Again, taking similar example, let's say we have 12 sub-channels, subcarriers available to us. We had 4 links, and then we decided to give 3 sub-channels to each of the link. So theoretically, if all channels are same, they should achieve same throughput. But what might happen is that if we look at link 4, we have the total span over which these subcarriers have been allocated is 8 subcarriers, and for link 3, the span is just 5. So why is the span any factor? So if span for link 4, if the span is 8, so receiver must be able to the RF front end must be able to receive this much bandwidth. So if the bandwidth is higher, the sampling rate at which it has to operate will be higher. And that's what happens, that if you have a larger span, you have higher sampling rate. And higher sampling rate, it turns out, it leads to higher system power consumption. ADC, these are the plot for ADC and DC power consumption for USRP devices. So which leads to higher system power consumption. So keeping this particular example in mind where we had 12 sub-channels, so this is, I'll talk about a small simulation where we had again 12 sub-channels, 4 links, and we formulated a maximum optimization. So we had these 12 subcarriers, we wanted to allocate it to these 4 links. So we created different channel environments. So these channel environments we created using 3 different kind of interferers. These interferers A, B, C were on different subcarriers, so as to create different channel environments, so that when interferer A is on, it would the SINR at the receiver N4 would be small. So this is just one example of it. So basically, we created different channel environment. We formulated a maximum optimization problem based on the channel coefficient that we get from this network.
So ABC are like primaries?
Not exactly here, not here. In this case, they were just used to, they can be primary. I mean, I could have chosen them to be primary, and that case, we would not use those subcarriers which are used by ABC. But the purpose here was, we just wanted to see the effect of spectrum span, and we wanted to create different channel environments. So basically, we had this topology fixed, the 4 links, and then we had these interference which would come on and off, and would give us different combination of these interferers would give us different channel condition. And we used the same channel coefficient from those calculations for this maximum optimization, rate optimization.
But the optimization is over N1, N2,
Yes.
right?
The optimization is,
Look, there's nothing stopping you from calling ABC as primary.
right.
But so they're just, they occupy some
Yeah, exactly.
subset of
They're just sitting there and we're
subcarriers.
trying to avoid them.
Okay.
Yeah. So for this maximum optimization, we added the constraint of span. So we said that if there are 12 subcarriers, the span cannot be more than 6, 7. So we tried different combination of it. So as you would expect, if we have a larger span, we would have higher probability of selecting a channel which is good for a particular link. So this graph is the output from, this plot is from one of the simulations where the x-axis is the span that we fixed in the maximum optimization, and the y-axis is the maximum rate that we could achieve for this 100 kilohertz channel. So as you would expect, these are different channel conditions. So the common thing is that if the spectrum span is very high, then your maximum rate is also high. The minimum spectrum span in this particular case can be 3, because then you have to allocate contiguous channels to each of the link. In that case, for all of the channel conditions that we tried, the throughput goes down. So, but one good thing was in almost all of our simulations, we found that you could still reduce the spectrum span to a small number without incurring a very large penalty. Like from the maximum, you can go to maybe 90% of the maximum, and without incurring a large penalty, you can probably operate at smaller span. So, and again, the span matters because it would result in lower system power consumption. So this was the first study that we did for about the system allocation, resource allocation, spectrum allocation. So the key takeaway that we had was that spectrum span would affect the system power consumption, and so we proposed that this span should be considered while allocating this spectrum. And then a simulation shows that it's possible to allocate spectrum in fair manner while restricting the span to a smaller value. This was published in DASPAN 15.
I didn't understand one thing in the previous slide.
Right.
So the simulation is, the exhaustive search is
right.
the main line, and the dotted ones are...
So the exhaustive search is, when we did the simulation, one we went through all possible combinations, actually in like a brute force manner.
Right.
The other one was, we used a mosaic solver which is much faster. So it basically says that if we want some sort of pseudo real-time implementation, it's possible even with some solver which is already readily available.
But my point is that the exhaustive search, often it is the case that what I found is,
Right.
you can't do exhaustive search, so you resort to one of these, and whatever you get is the best.
Yes,
And in this case, your exhaustive search is better than what the solver is giving you, so it's an artifact of the solver then, right?
Yeah, that is because the solver actually the whole problem becomes integer, sort of integer program, mixed integer program,
Right.
when we try to solve it. So it makes some assumptions about it. It relaxes some of the variables to continuous variables, and then again fixes it to, once it has solved for continuous, then it moves back to integer. So
Somehow, because you're looking for a max-min solution, you know that each of the 4 users should get three channels. Like that's somehow embedded in. Is that true?
no,
Or is it that you have different varying channel gains, and sometimes the solution only gives somebody 2
right,
channels?
like only 2 channels. It is possible that if the channel conditions somehow are created in a way that only 2 channels are sufficient for one and 4 for the other, it might allocate something like that. But at the end, the goal was maximum rate, so the throughput that can be achieved on that channel, that matters. Okay, so this study was about.
So is
yes.
it max-min rate over the channels or over the users, the pairs?
Over the users. That's why multiple
Okay.
combinations. Okay, so once, let's say using some method, the spectrum has been allocated, either considering span as a constraint or not. So once the channel has been allocated, then we can start using NC-OFDM. So the design that we presented, the network that we presented, the first problem that we faced was the asynchronous transmission. So we have the asynchronous transmission going on, and they result in sort of loss in orthogonality of NC-OFDM. So I'll discuss about that. So this is the similar setup, but it just basically shows the same thing. We have total bandwidth available to us, and some of it is occupied by primary user, rest of it's available to be used by secondary user, and then some allocation scheme has allocated these 3 links, 3 different allocations, 3 different non-contiguous allocations, right? And we assume that all of these transmissions are asynchronous. They do not try to coordinate with each other. So if we see that this transmission in time domain, it would look something like this. Again, we have 4 links and 12 subcarriers using the same example. If we have 12 subcarriers like this and we have 4 links, so in time domain, if we just focus on 2 links, so if you remember from OFDM like overview, there's one part is cyclic prefix, the other part depends on number of subcarrier, and the total is your one OFDM total symbol. So what happens is here in this case you can see that 2 OFDM symbols of link 1 are intersecting with one single OFDM symbol of link 0. So if link 0 tries to decode, it's within its own observation window. Once it identifies that this is my OFDM symbol and tries to decode it, it encounters 2 different OFDM symbol, NC-OFDM symbol for link 1. And that actually results in loss of orthogonality. This doesn't happen in case of LTE downlink. LTE downlink also, there can be multiple UEs. You can think of them as multiple UEs, but because there is a single transmitter, which is E node B, you don't have any asynchronous time offset between any 2 subcarrier allocation. So this particular effect actually results in inter-carrier interference. And this so there are 2 ways to deal with it. Either we provide some sort of guard band so that the effect of one link on the other is not so much, or somehow enable some sort of synchronization. So to characterize this interference between, because of asynchronous nature, let's just take 2 subcarriers. We assume that one link is using one subcarrier, other link is using just single subcarrier. Let's name them mu and m here. So in time domain, they might look like this. Again, you have cyclic prefix and the OFDM symbol, again cyclic prefix and then OFDM symbol, and then the offset between them can be random. And the offset is represented as tau here. So when we characterize the whole thing, and this plot actually shows how the interference looks like. This is an example when the value of n, the number of subcarrier is 1024, cyclic prefix is 256. So the total OFDM symbol length is 1280 samples. So it turns out that if the time offset is less than cyclic prefix, we do not see any intercarrier interference between these two subcarriers if the time offset is less than that. And that happens because cyclic prefix basically absorbs. That's what cyclic prefix has been added for. That's what it's used in regular OFDM to absorb effect of multi-part transmission, so there's no inter-symbol interference. But as the time offset increases beyond your cyclic prefix length, we see that if the subcarriers are next to each other, that is the delta m basically is the difference between the index of subcarriers. So if delta m is 1, it means that they are adjacent subcarriers. So they might have the maximum effect on each other. So as you can see here for delta m, here we get maximum interference with maximum value can be close to -7 dB. That is relative. Like if we are transmitting at 0 dBm, then the neighboring subcarrier would see -7 dBm power in its own transmission. So as the value of, as the distance between these two subcarriers increase, as you would expect, this value goes down, the interference goes down. So because we do not have control over this time offset, they are all asynchronous, we make assumptions that this time offset is uniformly distributed. Like we assume it to be uniformly distributed random variable. And then we calculate the mean interference power that is caused for each value of delta. So this is that mean interference. If we assume that the offset is uniform random variable and we calculate the mean. So basically the x-axis is now delta m, where if the distance between two subcarriers increase, we expect the interference caused by a particular, the interference would get smaller basically. So few things to note here is that if we divide the same bandwidth into different sizes of subcarriers, let's say we divide into just 128 subcarriers. So each subcarrier has a larger bandwidth compared to when we divide it to 1024 subcarriers. So the effect of this ICI is different. And why is that different? Because if you have 128 subcarriers, it means your time domain symbol is first of all small. So any time offset would affect it in a bigger scale compared to this 1024, in which case your time domain symbol would be, I think, like, I don't know, 8 times of that. So basically, because time domain symbol is very long, so the ICI, because of the asynchronous transmission, would not be as much. So two things to note from this is that even for the same bandwidth, if we choose different number of subcarriers, we see different performance. So this plot might suggest that it's better to choose a smaller, like more number of subcarriers. But then again, that will be limited by other factors. You can't have like infinitely long NC-OFDM symbol. So, and the other factor is, as you can see here, is that the effect of 0 subcarrier on n-1 subcarrier, because the transmission is happening in 0 subcarrier. You can still see the ICI because of this on n-1, and that happens because we have used this FFT matrix in between, and it's just because of the way the OFDM symbol is decoded. Right. So
the worst interference is at n/2, or is it that the worst? Is it that the worst is in the center or at the edge?
At the edge. So this is like a relative interference that you would see if you're transmitting at, let's say, 0 dBm. You would see -20 dBm in the like next subcarrier. But if you move away, you would see -60 dBm, something close to that. So as you move away, you...
Okay, so this is like measuring the interference from the adjacent subcarrier,
right.
2 over 3 over.
Yeah, but this is assuming that there is no frequency offset in the system It's just because the transmissions are not synchronous. And this is just between two subcarriers. Like the transmission is happening on one subcarrier. So,
and this is where the time offset is just averaged. It's uniform over this.
Yes.
Okay.
So this kind of analysis. This kind of analysis can actually be used to identify guard band between two different allocations. Because we know what would be the mean interference that we see because of from a particular subcarrier because of asynchronous transmission, we might, let's say we can tolerate minus 40 dB of interference from one of the in our subcarrier. So we might have to provide at least the small bandwidth as guard band. So this is just from one subcarrier. You can, if we allocate 2 or 3 subcarriers to one link, based on that, the more details are in, there's an example in Thesis where we actually calculate what would be the guard band size. And it turns out the guard band for when we are transmitting at much higher power, because the guard band requirement may be very large. And that happens because OFDM in time domain it has this sync out of band transmission. In frequency domain it has this sync out of band transmission, and if there is even a small shift here and there, the effect is pretty large. So the guard band requirements can become very large.
But somehow n over 2 subcarrier index difference, right?
Right.
Is the same number of hertz at 1024 is at 512. Like somehow you fix the
bandwidth.
You fix the bandwidth, so n over 2 subcarriers away is like always half the bandwidth away.
Yes, but they each see different. Like if you have 1024 subcarrier, you would see different interference than 120. So this analysis can be used to identify guard band, and the other way we can deal with the whole ICI is to actually enable some sort of synchronization, distributed synchronization. So this is an experiment that we did to actually try this distributed synchronization on orbit. So we had, what we did was, with these two links, so basically what we did was we added a low power beacon to the signal. So what it did was, if link 1 is starting to transmit using its own allocation, it will first sense that if there is a beacon present or not. Because it's a common beacon, it's the 1pn sequence, which is everybody knows, that's the assumption. So link 1 first looks for a beacon. If it doesn't sense any beacon, then it starts the transmission with a periodic beacon added to it. And this transmission in frequency domain would look something like this. If link 1 has this NC-OFDM allocation to it, it will be a low power underlay which is across all of the bandwidth.
Can you go back to the previous slide? So that, like, you know, over at the far left to the far right, things are kind of all jammed in there.
Yes.
I mean, is this picture saying like an asynchronous user at the adjacent subcarrier really is like a situation you just shouldn't tolerate? Like, is that like, is it going to 0 or is it going to -10? Like,
yeah, I mean, it doesn't go to 0. I think it's that number is still pretty high. Like if the adjacent one, I believe is close to -6 or 7 dB.
right.
So yeah,
And
you can
so
say that adjacent one you should probably avoid at the very least.
So out of your, when you optimize and do these optimized assignments, do you end up leaving an adjacent like a subcarrier empty between
Right.
two users, or?
Almost always, like whenever we try to allocate after the calculation, there would be adjacent allocation. I mean, there has to be enough gap between two transmissions. I mean, if we somehow synchronize the transmission, then most of the problem go away, because that's what LTE does. Like LTE has this.
Yeah,
one,
of course, but
yeah.
you're in a different world.
So, like I mentioned, so we add the beacon in the transmission. This is like a low-powered beacon which is periodically added to the NC-OFDM transmission. So any link which comes after link 1 will try to detect and it's pretty simple mechanism, but the good thing was that we actually implemented this on orbit. We could test it on real time. It was able to synchronize without any problem. So the result from this, we tried in a very simple topology. Where the topology was, we just had these 4 nodes, and there are two links, and each has been allocated to different set of subcarriers. We used total number of subcarriers was 64, the bandwidth was 10 megahertz. So initially we tried both transmitter to transmit almost at the similar power, try to keep the SNR at B and D to be same, a sort of symmetric environment. And what we found was if these transmissions are not synchronous, that is the top curve, the BER calculations, they show the performance is worse compared to when we actually enable some sort of synchronization in it. So this is something that we expected. The more interesting result that we found was when we try different SNRs, like one transmitter is transmitting at higher power compared to the other. So so one link was operating at SNR rho, and the other link was always operating at like 3 dB below that. The SNR that whatever we observed was 3 dB below that. So what we saw was that the link which was operating at higher SNR, which was link AB here, it did not see any impact of the whole asynchronous nature, as you would expect, because it already has good SNR to it. So there was not much different, but the link which was operating at low SNR, it saw a good improvement over asynchronous transmission. So what this basically says that it's always advantageous for links operating at low SNR to try to synchronize this transmission with the link with probably higher transmission. So the method which tries to detect beacon, and so that would still be applicable because the beacon which is maybe is being transmitted at much higher power, which would be easily detected, and it's easier for a new link entering the system to synchronize. So,
but the beacon would be affected with the same SNR difference, right?
Beacon would be affected
by the same SNR differential, right? Meaning the receiver would receive the beacon at the lower value as well, lower transmit power as well.
No, so there's only one beacon. The other link which is trying to synchronize would not even send a beacon.
I see.
So it's almost like one of the link takes a role of master where it's transmitting beacon and the others are, whoever can hear it, synchronizes to it.
No, but my point is if link 1 is, if A is the source of the beacon,
right,
and the receiver of the other link which is operating at a lower SNR,
right,
would somehow the channel impact the beacon as well? No.
Yeah, I mean, it would impact, but beacon itself is first of all periodic, and A is sending it, sorry, the other, itself is very periodic, so it's not like it's, even if it's not affecting all of the time. So,
how big was the sequence, the beacon sequence that you used?
I believe either 64 or 1.8.
64.
Yes, because we could not process larger ones in real time, so either of those. So the key takeaway from this analysis was that the time offset between different NC-OFDM transmissions result in some ICI because we lose the orthogonality in the system. And we can potentially calculate the guard band using our analysis. We also showed the decentralized synchronization scheme, and we found that the timing coordination using this scheme is especially beneficial when there is asymmetric condition, which hopefully would be there in a regular system. So this is, so far I've talked about the allocation and what happens when multiple links are using NC-OFDM. So even for a single link to successfully decode NC-OFDM signal, it needs to perform some operations. Like we saw in the OFDM overview that it needs to do frequency offset, time offset calculation. So
So I have a question here. So suppose you have a SDR receiver.
Right.
Is it possible to do the synchronization after the fact? You receive both signals and then shift one of them to match your timing without having to do any coordination?
Yes, so that is what we did with USRB. So
Without beacons?
oh, without beacons.
Okay. Yeah.
So then we had to match the clocks between the
Yeah,
relay.
but you'll get two signals and then you can play with the preambles and then figure out how much timing offset you have and then do it without, but that's kind of zero beacon approach.
Yeah,
Only
I
with
guess,
SDR you cannot do it normally.
I guess you can identify some feature from one of the transmission. And then, yes, but yeah, we tried only with. So, like I mentioned, for the offset estimation, we so the problem of frequency and time offset estimation for a single NC-OFDM link, we designed a control channel which enables us to enables us to calculate those offsets. So generally for a single link, the requirements are that you need to be able to calculate frequency offset so that you can decode it. In case of OFDM symbol, you should be able to identify when the OFDM symbol starts. So OFDM symbol timing estimation is also important. And then the question comes, why can't we use whatever is being used in the OFDM? So OFDM for frequency and time offset basically uses repetition in time. So it does the autocorrelation of signal, whatever it receives, and then identifies the features from that. But the repetition cannot work in system like this because at particular receiver you might be seeing 3 different transmission in the same overall bandwidth because everybody is using some set of subcarriers within the same bandwidth. So if you perform autocorrelation, then you would not be able to identify correct features. So that's why we are not able to use whatever traditional method that we had for OFDM. And then another requirement could be the exchange of some sort of control information between transmitter and receiver, so that something along like subcarrier allocation. If one transmitter chooses to change it, then it should be able to transfer that information to receiver. So both of these problems we tried to solve with this in-band underlay control channel. Again, it's the same as in frequency domain. We added the same underlay control channel which spanned the whole bandwidth. So it had 2 purposes. Again, like we mentioned, it could carry the control data, whatever is required, and then it can also aid with timing and frequency offset estimation for a single link. So if we see how this underlay transmission looks in time domain, this is how it looks like. So this is just the underlay part. So this signal will be actually added to NC-OFDM signal. So this is a very low power transmission which is going on. In time domain, it has basically 2 modes. Mode 1 we used for timing and frequency offset, and mode 2 we used for regular control channel information. So even mode 1 had these 2 parts where we had this short PN sequence which were repeated n times, and then we had a very long PN sequence. The short PN sequence we use for frequency offset and the long for time. I'll go into detail of how we actually calculated it. So again, if we see the underlay, the same from previous figure, the overlay data, that is the NC-OFDM data, is on top. So basically we add the sum of these 2 signals. This is happening at much lower power. So in mode 1 operation, what we do here is that we first correlate with short PN sequences. Because these are very short PN sequences, we don't see a very good correlation output out of it. But what we can find is, using this formula, that what would be the frequency offset in the system. So we calculate the frequency offset from this repetition of short PN sequence, and then we correct the frequency offset in the long PN sequence. And we do that, so once we correct the frequency offset in the long PN sequence, we get a very good correlation from the long PN, which was not possible without correcting frequency offset, because the frequency offset rotates all of the constellation. So once these 2 stages are complete, we are completed, we actually find the OFDM boundary. So we arrange this underlay channel in a manner that just when the long PN sequence ends, it matches perfectly with the OFDM symbol boundary. So we not only get the frequency offset, we also get perfect time offset calculation from this. So this we implemented again on USRP. This was a GNU radio architecture where this regular OFDM system, we added this regular NC-OFDM system, we added this underlay encoder, and the receiver side we had this frequency and time offset calculator added to it. With again.
What is this? Yeah, what does that mean? That you have this underlay encoder and it feeds a data stream to.
Yeah.
I was kind of trying to understand.
So in this figure,
how this really works.
So this is one complete OFDM symbol.
Right.
So which has cyclic prefix and regular OFDM part to it. So once we have, because we want this underlay channel to synchronize properly with this NC-OFDM part in time domain. So just when we have added the cyclic prefix, we bring in the underlay and we arrange it in a manner that it matches perfectly with. So basically it says that that is the part where we also add the underlay. Just when we add the cyclic prefix, we also add the underlay in a manner such that after long PN sequence we can detect the boundary.
I hate that. I'm really an idiot. So is the underlay kind of like a multi-carrier CDMA? Is it like, so what's doing the spreading like in the underlay?
So in case of OFDM, like one OFDM symbol is I believe like n samples long.
Yeah.
Right. So that n samples long corresponds to one subcarrier. I mean, if you see it in time domain and frequency domain. But if I spread in frequency domain to all of the bandwidth, then my one sample would be equivalent of this.
So you're asking how you're spreading?
Yeah.
Tell him how you're spreading. Why are you answering something else? I think he's asking a very straight question, right?
Yeah.
I mean,
like what? How is
so
the spreading really occurring? Like, is it that you?
So each sample of OFDM, if you add one chip, right? So if you just add one chip to each sample, so basically if you have 1024 subcarriers and we use 1024 PN sequence length, right? So for
you'd have a chip sequence that's length 1024.
Right, and that would.
And you send either plus that or minus that is added to the OFDM.
Right. So we basically add the signal to it, literally, like because when we have it in software, we simply add it to it and we are able to recover on the other.
And this thing is like the amplitude of this thing that's added is small compared to.
Yeah.
Do you have a picture?
Not for that, but
so
yeah.
in terms of like if he just turned off his actual data system, it's like what we used to call multi-carrier CDMA, where you did the CDMA over OFDM subcarriers.
No, it's not.
Is it?
He's not even doing OFDM. He's just doing a DSCDMA signal and just adding it to the OFDM.
But he's adding it into this in.
It's in time domain. Like I'm adding it here. It's not before IFFT.
Oh, it's in time domain.
Yeah, he's just adding it. That's all.
So okay, so basically.
Unless you were asking something
okay,
else.
so no. Okay, so now maybe I understand why I'm brain damaged or something. So okay, so you do IFFT and then in time domain.
Yeah.
You add. Okay. All right.
All
So
you do
you're
is add it.
literally adding.
You're only adding the same sequence, right? There's no data modulation.
Well, there is like a plus or minus a bit of data modulation.
Some control information you could.
Are you sending control information as well, or just
So-
adding the same PN sequence?
So at least for frequency time offset, it's the same PN sequence. But for control, we can modulate. That's the second part.
So you could do this in over. You could have done it on the left in frequency, added something to each frequency domain component, like a small signal,
yes.
and like a.
Yeah. So
No, but
someone wanted the MCCDMA is the word.
No, just.
No, but that is difficult to decode at the receiver. Then you have to know where the proper OFDM symbol boundary so that you can decode it correctly. I mean, that was the whole problem to begin with.
Okay.
Right. Not a good idea.
Okay,
Okay.
so this was the architecture that we used for USRP implementation. So I'll just go over two brief results. So we measured the performance of this underlay time and frequency offset estimation by two metrics. One was probability of false alarm and probability of misdetection of when we can correctly find the OFDM symbol timing. If we cannot find it, it means there was a false alarm, or if we missed it, then it's a misdetection. So we want both of those values to be a small number. We tried different combinations of short PN sequence, long PN sequence, and different values of repetition. So these two figures, basically the LS is the different values of short PN sequence, the x-axis is different values of long PN sequence. So what we found was because we did the experiment only on 1 megahertz, the result was not extremely good. Probability of misdetection was still 0.1. But if we extend the same result to, let's say, 10 megahertz, where you are able to transmit much longer PN sequences, you can reduce this probability of misdetection to further small value. So what we found was it was possible to get some parameters, some combination of short PN sequence, some values of repetition, and long PN sequence, which can calculate the frequency offset correctly and also determine the value of OFDM symbol time offset. So this was for the mode 1 result. The mode 2 was our regular CDMA transmission data, where we sent the data, and we were able to achieve close to 11 kbps over all of the 1 megahertz of bandwidth. So we were able to observe both of these results, that we can calculate frequency offset, we can calculate correct time offset, and we can somehow send data across this channel as well. So this was the secondary result. Because we had a channel which is available to us, why not send control channel as well?
So this direct sequence signals using the entire band, right?
Yes.
And if there's like a primary there, it's creating a little interference for him or not?
Yes, it will create. So
don't you have these results of what the control channel?
no, it's
Oh,
actually
you haven't gotten there yet?
I removed that particular plot because the talk was, I tried once, it was going to like
Yeah.
1 hour 30 minutes.
But you should tell them how many dB below noise it is.
So the difference between the NC-OFDM and underlay channel, we kept close to 10 dB, and then we ran this experiment, and we were able to get close to 11 kbps. And this is because
so we keep it 10 dB below the data signal.
Right, but that's the data signal generated by this secondary
Yeah.
user, right?
Right. And this is just over 1 megahertz, so we could not play with PN sequence, much longer PN sequence. But if we had done it over a longer bandwidth, we might have achieved better rate and better
So in fact,
performance.
there's this research thesis I want this guy to do, right? Where is he? Zhu. You completely go revive all of multi-user detection and interference cancellation. You want to recover this really weak signal from a lot of strong interferers. Right?
Yeah, right.
Okay, so the key takeaway from this study was that traditional method of
Think about it.
I'm sorry for laughing. I'm just looking around the room thinking, oh, like, who in a sincere would know anything? Like nobody.
I told him for 4 months to look at it, and he has not made progress because he thinks he does not know what it is.
Well, he doesn't know, right? No one knows.
No, now he's reading stuff. But it seems like it should be an easy problem to cancel really strong interferers, right? That's something we always knew. Remember Jack Holzman's argument of interference cancelers? Make all the strong guys cancel them out first. So I think you should recover.
Successive interference cancellation does the two.
That's what.
Well, it's
so
really-
it'll work pretty
yeah.
well because you have a really weak signal that you care about.
Right.
And there's a lot of strong interferers, and you can successively keep cancelling them out. That's what I'm saying.
Right, but there is a pattern, right? There has to be a particular, if all of the impending signals are at the same level or something, then it becomes difficult. But if you've got like enough
Yeah.
differentiation between them, you can
There's some
do
interesting questions to ask there. Right?
Right,
In terms of,
right.
But at least the signal you care about is really weak. It's 10 dB below everything else. Yeah.
Oh, this reminds me of another question, which is, in this world where there's a primary, right, you had these the results say, oh, like the adjacent subcarriers, you know, when it's transmitted asynchronously is a real source of interference. So somehow you want to avoid using adjacent subcarriers with respect to the subcarriers used by the primary.
Most likely. I mean, the way
when you do these optimizations, do you have some kind of a, you know, like, essentially embed kind of the interference that you cause to the primary by asynchronous operation?
So in asynchronous case, some part of the the ICI arises because the other guy is also using FFT based system.
Right.
So if primary is not using it, then.
But it might be, right?
It might be. So in that case, yes, you would have to provide it.
Okay. All right.
Yeah. So we proposed this underlay control channel, which enabled us to calculate frequency and time offset, and we presented the feasibility of this design using both simulation and experiments. So the last section, we found some nice security features in NC-OFDM for low probability of exploitation designs. So generally there are few metrics which are by which we measure how secure a particular transmission is. So those are low probability of detection, basically saying that keep the power below certain threshold so that it cannot be detected, such as DSSS. Low probability of interception, signal can potentially be detected but won't be intercepted, it cannot be tracked, such as fast frequency hopping. And then comes the low probability of exploitation. It means signal can probably be detected and intercepted, but you don't have enough parameters available to you to decode it. So because you don't have that, it's not possible to spoof it as well. So generally these are the parameters by which measure the security of transmission. So how does NC-OFDM perform in this case? So signal detection, it doesn't do well because the SNR requirement for OFDM signal to operate it make it difficult to hide it below noise. For signal interception, finding center frequency, we want to find what is the center frequency. It's not so straightforward because if we simply look at one particular allocation, it may happen that we have given it some weird set of subcarriers so that the eavesdropper cannot identify where the center frequency was. And similarly, bandwidth also cannot be, the total bandwidth cannot be determined directly. So this was just one example where we had this, this is the data that we actually collected from USRP, which had total 20 megahertz of transmission, but we chose to transmit only on the middle 10 megahertz. And even there we had some contiguous allocation and some interleaved transmissions going on. So in this case it's not possible to tell that if it is just 10 megahertz of OFDM signal transmission going on, or there was total 20 megahertz and we are choosing to transmit only on the middle of the subcarrier. So, and if we don't know the total bandwidth, the correct sampling rate for, like, if we want to use regular OFDM decoder, NC-OFDM decoder, then it's not possible to do it directly. So it becomes slightly difficult in the case of signal interception. For the signal exploitation, we have to find correct OFDM symbol length so that we can, first of all, parallelize it and feed it to an FFT. We have to find cyclic prefix length so that we can remove it before we feed it to FFT, and then we have to find out which particular total number of subcarriers to begin with, and then which particular subcarriers were used by the transmissions. So generally for this kind of calculation, for a regular OFDM symbol, there's something called cyclic autocorrelation function is used, which reveals all of these parameters. So what is cyclic autocorrelation function? So if you have a signal, perform the autocorrelation, because for OFDM it turns out this autocorrelation function is periodic, and because it's periodic we can represent it as the Fourier series, and the coefficient in this Fourier series is your cyclic autocorrelation function, which is basically a function of two values. Alpha is the cyclic frequency, tau is the lag in the autocorrelation. And this alpha is basically nothing but alpha n is n over t naught. This is one OFDM symbol which has cyclic prefix, and this use full part, and this is a total value. So the cyclic frequency basically is 1 over this t naught value. So if an eavesdropper collects data over more than Nyquist rate, it can determine, simply by autocorrelation, it can determine some of the values. So this is how the cyclic autocorrelation function looks like for a regular OFDM transmission. This is a function of lag tau and a function of cyclic frequency. This is a normalized cyclic frequency actually. So what can be determined from this plot is that simply if we see the middle row, if we simply perform autocorrelation, through this A we can determine what is the useful symbol duration, this part, which basically tells us if we have the information about bandwidth beforehand, we can find out how many number of subcarriers we are using. And once we have found out this peak, if we traverse in the other direction, we fix the value of tau and traverse in the other direction, we can find this cyclic frequency, which would determine your T naught, because it's the inverse of that. So once you know T naught and TU, you have both information. Now you can remove the cyclic prefix and then try to decode it. So this is what you can do with a regular OFDM transmission. In case of NC-OFDM transmission, if we, for some reason, if the allocation is contiguous, it looks pretty much same as OFDM transmission. If there is interleaved transmission, interleaved allocation, it turns out that you see so many more peaks that simply finding out TU is not straightforward. So if we see here that we have multiple peaks when the cyclic frequency is 0. So there's more ambiguity there. And if we choose some random allocation, in that case, a lot of features go away. So basically, it becomes more and more difficult in case of NC-OFDM to find these features to decode the signal. So I have actually in Thesis there are more results about what we have done with the security features. But the key takeaways are that if we avoid the use of corner subcarriers, it becomes difficult to identify the total bandwidth, and then impacts the down conversion, and you have wrong sampling rate with you. So it becomes difficult for the interception part. As we use some combination of contiguous or interleaved subcarriers, it complicates the cyclostationary analysis. It creates more ambiguity. And there are some other techniques which can be probably used, that is some random size of cyclic prefix added between two symbols. And at the end, these OFDM symbols are nothing but some linear combination of the data that we have fed to a FFT matrix. It's just, if we keep reinitializing the set of subcarriers before time elapses, we can probably make this analysis more difficult. So this is the complete presentation where discussed like most of the research problems that are dealt with NC-OFDM and spectrum allocation with non-contiguous spectrum. So the summary is that we saw that the spectrum can potentially be non-contiguous, and we have proposed use of NC-OFDM as candidate. We highlighted the effect of spectrum span, and we found that ICI can arise from asynchronous transmission. We can use that for Guardman calculation. We have also proposed the underlay control channel for frequency time offset estimation, and we have identified some security features which are present in NC-OFDM transmission. Some other research project that I've worked on is the whitespace spectrum allocation for whitespace channels, and then LT radar coexistence in CBRS band, LT Wi-Fi coexistence, also part of DARPA Spectrum Collaboration Challenge. So this is it. So I'd like to, if you don't have any questions.
So in this question with security,
Yes.
like, so you use words like, oh, it makes it more difficult.
It's not quantified.
So if somebody were like, is the goal to quantify this, to say, well, how long do they have to watch, listen, in order to resolve? I mean, if you keep transmitting a really long time, eventually,
Right. So
right,
that's what, like,
it's resolved what you're doing, isn't it?
if we keep reinitializing the set of subcarriers, then you can always fool it. But at the end, you
Do
can.
you know that? I mean, is there math that says,
Okay,
like
that
if you
statement,
reinitialize every?
So go back to your slide. So did you say LPE or no? You did
Yeah,
that, okay.
LP, like exploitation. So at least the reinitialization part is, I think mathematically it can be shown that because at the end, like I said, it's a linear combination of the data that get fed to the FFT. If you change that linear, before the other person can decode and find out which particular components have been used, which coefficients were non-zero, if before that you can reinitialize the whole subset, then
So for instance, how did your receiver find out how all of these things, like your intended receiver?
that has the information about which subcarriers are being used. They've already agreed upon.
Yeah, but how did he convey that? Oh, how we agreed on all of this stuff, you know?
Control
and
channel.
Huh?
The control channel.
So, but why isn't your attacker not allowed to observe this control channel? If he observes the control channel, then all of this is irrelevant. These features.
If it can decode the control channel, then again then it already knows all the information. It can directly decode it. But assuming that eavesdropper, like we have some assumptions about eavesdropper that it, at least to begin with, doesn't have
No,
access to
but
control.
that's the whole point of a control channel being spread spectrum, right?
Right,
Is that
underlay.
you can't do any better than that.
But there's always if the receiver can listen to the control channel, then you know, I mean, I'm not a security person.
So-
But there's a
No, so there are-
you start with an attack model. And
Right, so this is
threat
how this came about, right? Is that we first kept using the term LPI when we started doing this work, and then the guys at the ONR laughed at us and said, "You guys have no idea what LPI is.
Right.
What you're doing is what is called as LPE." That's why I asked him if
Low
he
probability of
exploitation. It's completely different from
Intercept.
interception, right? Or sort of basically
Detection.
LPI or LPD, right? Is basically saying that can I even detect this signal? And for that, they're saying the only thing you do is basically spread like hell. That's all. They can still detect you if they can detect your energy in spite of you spreading and kind of trying to stay, invisible. Then they're detecting it. So therefore, they said anything you're doing with this can never be LPI or LPD. So we learned this actually. I mean, I gave a presentation and those guys said, "What are you talking about?"
Right.
And then so they said the terms you want to use are LPE, and so what he has talked about is purely exploit. So exploitation means can I recreate that waveform? That's sort of the idea.
Right.
Can I figure out what the amplitude is, what the modulation is and all that and try to spoof that signal? So LPI, the only thing you can do is, for LPD, the only thing you can do is essentially be low energy or do some frequency hopping, which is same. Direct sequence or frequency hop spread spectrum. That's the only thing you do. So which is why the control channel, we put it there. And if they catch the control channel in spite of your trying to be LPI, LPD, then you're toast. I think the greater point, right, I don't know if you mentioned this, I say this every time I talk now after I've learned what this means. OFDM is a sitting duck. And everything 5G is about OFDM, or any modern communication system that you can think of is OFDM. And OFDM is basically a sitting duck in that everything you know about the signal is out there because it's doing the same thing over and over again over a contiguous band. So the whole question was, can we sort of buy some new capabilities with LPE using this non-contiguous? And the control channel, if it gets attacked, that means you don't even have LPD, right?
Right. So this is for environments where there aren't laws about Well,
Right.
What is the order of magnitude of complexity to check all the possible parameters? Suppose I can store it in my
Yes,
software
we had this.
failure, right?
Yeah. Then
So how many, what's the matrix you have to check through?
yeah, we didn't quantify the whole thing, but yeah, see, like we can identify. All we have to do is identify number of subcarriers if you observe long enough, and then try all different number of subcarriers. Because usually number of subcarriers is in 2 to the power something, so the number can be pretty small over which you have to search. But if we play even with that we
And
don't
you might
choose.
have 2 dimensions, like which ones are being used also is another.
Yes. Okay. More questions? So then I would like to thank all of these people, Professor Mandayam, my advisor, for guiding me through these 5.5 years, I guess. Ivan, without which like most of the students would struggle at WinLab. Gokul for so many useful discussions, all my committee members here. I'd like to thank Office of Naval Research for funding my research for 5 years now, and all my lab mates. So again, I realized that I haven't spent this amount of continuous time in a single place, so thank you all.
So how does that make you feel? He said, I've never spent this much time in a single place.
so what, before the 5 years at WinLab?
Yeah, no, never.
Yeah.
I've moved a lot.
Yeah. So I never spent as much time as I've spent here.
Same here.
Yeah.
I don't know when you crossed that threshold, you know, like it.
No, I crossed it a while back, right? So I crossed, I mean, for a long time I would say, I've not spent enough time in this country, but now I've spent more time in this country than in the country I grew up in. Right?
Yep, that is a milestone.
So I cannot pretend
Right.
ignorance anymore.
I recently crossed that myself.
There are all these weird. Someday you'll be like, oh, I've been more time married than not. I think you're not that far from. You'll be there in a couple of years. No?
Probably, yes. Yes. And I hope it's more. Not enough. Okay, any questions? Okay, thank you. So I think we can have a closed session with Ratnesh. Do you have any questions for him? Where is Ivan?
He was here, like he came in between.
Are we still recording?
I don't know.
Sometimes he would watch in his office.
I mean, it streams on. Yeah, it streams on YouTube and then.
Thesis should be recorded.
Is it done now? Should that stop?
I don't know, Jake is handling it.
Hopefully,
Hopefully,
our private deliberations on YouTube.
they can remotely stop it, I guess.
Can you ask Jake?
No, okay.
Turn it off. Yeah, so that control channel should be secure because it's PN sequence that's
No, I mean, no CDMA control. I mean, that was. My sense is these things are debunked, right?
No, it's not debunked. The army and the military still uses.
What
That's all they use.
choice do you have?
That's the
It's
only
not-
thing they use.
But it's not CDMA, it's just spread spectrum.
Spread spectrum, that's all it is.
Yeah.
So in fact,
He's sending on a PN sequence. It's CDMA in the right
So-
signal
so-
space.
so we go every year and